In the vast cosmic theater, countless worlds orbit distant suns. Our search for these exoplanets began in earnest in 1995 with the discovery of the first planet orbiting a star like our own. This landmark finding introduced us to a bewildering new class of world, the hot Jupiter. These are gas giants, similar in mass to our own Jupiter, but they exist in scorching hot orbits, completing a full circle around their parent stars in a matter of mere days. Such proximity to a star's intense heat and gravity is a puzzle. Scientists now widely believe that these planets couldn't have formed where we see them today. Instead, they must have been born in the colder, outer regions of their planetary systems, much like Jupiter in our own solar neighborhood, before embarking on a monumental journey inward. How could a planet undertake such a colossal migration? Astronomers have proposed two primary theories to explain this epic journey. The first is a chaotic process known as high-eccentricity migration. In this scenario, gravitational nudges from other massive objects, like a sibling planet or a distant companion star, violently distort the hot Jupiter's path into a highly stretched elliptical orbit. Over eons, as the planet repeatedly swings close to its star, powerful tidal forces act like a brake, gradually pulling the elongated orbit into the tight, circular path we observe today. The second, more placid theory is disk migration. This process suggests a much gentler inward spiral. Here, the young planet is still embedded within the protoplanetary disk of gas and dust from which it formed. Like a ship dragging its anchor through water, the planet interacts with this disk material, loses orbital energy, and slowly drifts closer to its star. For years, distinguishing which migration path a particular hot Jupiter took has been a formidable challenge for astronomers. The key observational clue was thought to be the alignment between the planet's orbit and its star's rotation. The violent gravitational kicks of high-eccentricity migration would often knock the planet's orbit askew, resulting in a significant tilt that we could measure from Earth. A smoothly migrating planet, on the other hand, should remain neatly aligned with its star's equator. However, the story is not so simple. The same powerful tidal forces that circularize an eccentric orbit can also, over immense timescales, realign a tilted one, slowly erasing the evidence of a chaotic past. Because of this cosmic cover-up, even a perfectly aligned hot Jupiter doesn't definitively prove it followed a gentle disk migration path. This ambiguity left astronomers without a reliable method to read the planetary history books and uncover the true story of their formation. To break this long-standing deadlock, a new observational strategy was needed. Their method zeroes in on the final stage of high-eccentricity migration, the circularization of the planet's orbit. The time it takes for tidal forces to transform a highly stretched orbit into a circle is not instantaneous. It's a process that can be calculated based on factors like the planet's mass, its final orbital period, and the physical properties of its star. The crucial insight is that this circularization must be completed within the total age of the planetary system. If a hot Jupiter is found in a circular orbit, but the calculations show its circularization would take longer than the system has existed, it presents a paradox, a clear sign that it couldn't have arrived via high-eccentricity migration. Applying this novel test, the researchers analyzed the circularization timescales for a catalogue of over 500 known hot Jupiters. Their calculations uncovered a remarkable subset, approximately 30 planets whose orbits are nearly perfect circles, yet their theoretical circularization times far exceed the ages of their parent stars. These planets are cosmic impossibilities under the high-eccentricity model. They simply did not have enough time to settle into their current orbits through a chaotic process. This finding provided the first strong statistical evidence for a different origin story, pointing directly toward the smooth, steady path of disk migration. Furthermore, these specific planets display other characteristics that reinforce the disk migration hypothesis. A significant number of them have orbits that are well aligned with their host star's rotation, just as one would expect from a placid journey inward rather than a violent gravitational reshuffling. Crucially, several of these hot Jupiters are not alone. They are members of multi-planet systems, sharing their stellar neighborhood with other worlds, Such fragile, orderly systems are highly unlikely to survive the gravitational chaos of high-eccentricity migration, a process that would often destabilize orbits and eject neighboring planets into the cold darkness of interstellar space. The survival of these planetary siblings is a powerful testament to a more peaceful history. Identifying these special worlds, which still bear the subtle imprints of their formative journey, is a critical step toward a complete theory of how planetary systems form and evolve. They are pristine laboratories for understanding the diverse architectures of solar systems across the galaxy. By studying the chemical compositions of their atmospheres in the future, astronomers hope to uncover new clues about where in the protoplanetary disk they were originally born. These findings promise to peel back another layer of the mystery surrounding hot Jupiters, offering profound new insights into the cosmic origins and intricate life stories of these enigmatic gas giants.